All right, this is Honors Algebra 2 Pre-Calculus, and this is 12.5 in Algebra 2, our last video in Chapter 12. So we're going to talk about normal distributions. Normal distributions of data vary randomly from the mean, creating sort of a mound-shaped pattern, okay? So it's symmetric about the mean when graphed. Common examples of normally distributed data are humans' heights and weights, right? So the model obtained by drawing a curve through the midpoints of the histogram bar graph, right? So you can see if you draw this curve, that's called a normal curve, and that's pretty standard when we talk about a lot of data. You'll hear normal curve a lot. So a normal curve is defined by the mean, right, and a standard deviation, right? So in the standard normal curve, right, the one that we see most of the time, the mean is 0, right? So that's our y-axis. And then standard deviation is 1, so you can see that there are 3 standard deviation graphs here, graphed on either side of the mean. So recall from 12.2 that a relative frequency histogram actually gives us probabilities. So you can use the area under this curve, which is a process that we learn to find in calculus, but for this we're going to use our calculator because you're not expected to know how to do that when you do this. And you'd also use a calculator or a computer if you were doing this in most statistics classes in high school or college. So you can approximate you can find the area under this normal curve, right? This blue area right here, to approximate the probabilities of things. So the total area under a normal curve is 1, meaning that there's 0.5 area on the right-hand side of the mean, and there's 0.5 on the left-hand side of the mean. So this table here allows you to do something that you're not able to do by yourself just yet, which is it approximates the areas. So obviously the area at 0 is 0 because there's no width, right? The area up to 0.2, which would be like right here, right? That area is apparently 0.0793, and it would be the same on the other side, right? It would also be a 0.0793 if you're going to negative 0.2. And if instead you were going to 0.4, which is here, that area would be a 0.1554, and so on, right? All the way up to, they give you up to 2. So what we're going to do is we're going to use this table, which I'm going to copy on the next slide, to approximate some probabilities. So notice that I have this copied here. So and we'll walk through how to do this on a calculator as well. But we're going to approximate each probability using the area of this table, or the area under the curve, and this table that we're given. So let's start with the probability of 1.6 or greater. Okay, so let me switch this to a highlighter for a sec and make it a little bit tinier. Okay, so 1.6 or greater, so like here's sort of 1.6-ish, that's saying this area here, right? That's saying this area here. That's the probability of 1.6 or greater. That's the area I would need to find. So here's the argument. The argument is that I know that this entire side, right? I know that this entire side here is 0.5 in area, right? That whole side. But I was told that this area from 0 up until 1.6 was 0.4452. So the blue area must be, so the area that I want must be the 0.5 that exists on this side, this entire side of the graph, right? Minus the 0.4452 that's being used up by this white space here that's up on the table, right? So if I do 0.5 minus 0.4452, I'm going to get that this probability is approximately 0.0548, right? Or 5.48% if you want to write it as a percentage, right? So again, what's happening is I know the entire area on the right side of the mean should be 0.5 because the whole area under the curve is 1. And I know that from 0 to 1.6 took up this much space right here, which was 0.4452. So this must be the space that's left over, right? It also makes sense it's a pretty small percentage because as you get to the tail ends on either side of a normal curve, you're getting much lower probabilities. And we'll talk about how to do this on a calculator in a sec. So let's now, let's go ahead and do this one, right? So let's talk about the probability of -2 to 0.4. Well, here's -2, right? There's that -2 to 0, which we'll talk about in a sec. And then here's up to 0.4. So basically, here's the idea. Let me actually switch colors for a sec here. This section, right, would be the area up to 0.4. So this green section should be that area. And the yellow section, right, the yellow section that goes to -2, well, that should actually be this area, but on the other side, right? So the yellow section and the green section, right? If I find the area of each of those, remember they represent the probability. This is a 0.4772, and this seems to be a 0.1554. So if I add those, my probability is approximately 0.4772 plus 0.1554, right, which I can add together. So 0.4772 plus 0.1554, and I get that there's a probability of 0.6326, which would be 63.26%. Now, there's a way to do this on a calculator. Obviously, you wouldn't have been able to do this without the given table, right? Unless I show you how to do it on the calculator. You wouldn't be able to do it on a table, but let's scroll down and see how to do it on a calculator. I definitely had to look it up because this is not a thing that I, as a primarily calculus teacher, do a lot of the time. So if we wanted to do this on a calculator, there's a way to do it. So I'm going to walk you through the steps, but again, I had no idea how to do this until I looked it up. So what we can do, I'm going to clear all this stuff out, right? If you go to distribution, which is over VARs, see it says distr, right? So if you go to second VARs and pick distribution, you can pick normal CDF, which stands for normal cumulative distribution function. The cumulative is the part where you're adding, okay? So the cumulative is the part you're adding, so you can pick 2, right? You can pick that. And then notice that mine looks a little bit different, and that's just because of the generation of calculator that I'm using, right? But the number that they want you to put in is the lower bound. Well, the lower bound was 1.6. And then here's the trick. They want you to put in an upper bound. Now, you'll notice in the keystrokes that are listed here, the upper bound they put was 10 to the 99th. But the upper bound we have is none, right? This says x is greater than 1.6. There is no upper bound. So the reason that they picked 10 to the 99th is that's essentially infinity for your calculator, right? So you can do that. You can pick 10 to the 99th. They just want you to pick a number that's big to mean essentially infinity, right? That U symbol, right? That U symbol is going to be the mean. So this thing is the same as this thing, right? That's the notation your calculator is using. So that's the mean, and you can see that here. The mean is 0, right? And then the standard deviation is 1, but that's going to stay the same. Standard deviation is 1. And then we can go ahead and hit enter, and there you go, right? So I hit that, and there's my value, and sure enough, it gives me a value that's very similar to this. So basically, someone did this math for you and put this in a table. If you didn't have a calculator, you could use this table to figure out approximate probabilities. You can find it more accurately by putting it in your calculator. If you did the second one, right, if you did the second one the same way, so if you went to second VARs and went over to, sorry, I didn't want draw, I wanted normal CDF. Here, this one starts at -2, right, and it goes until 0.4, right? And then again, the same mean and the same standard deviation, and I hit enter, and you can see that I get the same value I got from using the table, just slightly more accurate, okay? Again, I didn't know how to do that on my calculator. I certainly don't expect you to naturally know how to do it on your calculator. There's a whole bunch of functions that your calculator does for specific branches of math that you either use a lot of or you don't, and if you don't do a lot of stats, you're not going to use a whole lot of this stuff. All right, so let's try this again. We're going to try it with a different set. So you're going to go ahead and try and find, using the area, the probability for -0.8, and we can check this on our calculator in a sec, so less than -0.8, which would be, that's sort of here, right? That's this section, right? You're going to find that probability, okay? And then you're going to do the same thing. This one's between -1.2, which is like here, and 1.6, which is sort of here, right, give or take. So for this one, you're probably finding 2 areas, right? We've seen that before, that you're going to find the 2 areas. So go ahead and give it a try, and I'll walk you through it too. So for this one, I know that this entire side has an area of 0.5, but I know that the area up until 0.8, right, is that this area right here is a 0.2881. So the probability I want is the 0.5, that's the area, right? The total area is the 0.5 minus the 0.2881, and that's going to give me my approximate probability. So 5 minus 0.2881 is going to give me the area under this. Oh, sorry, I didn't mean to make it 5. I meant to make it a 0.5. That's why that was very, very wrong. Second insert point, sorry, and then second insert minus, because I deleted that too. Come on, brain. Listen, people, you can't take me anywhere. Second, enter. So at least you should notice if you're getting things wrong. There we go. Okay, for the win. So 0.2119, which is a 21.19% approximately, right? If I do this one, right, the blue area is going to be from 0 to a 1.2. Well, that's this, right? So the blue area is going to be a 0.3849, plus the purple area is from a 0 to the 1.6. Well, that's going to be a 0.4452. So 0.3849 plus 0.4452 should give me approximately an 83.01%, right? So 83.01%. And you'll see that that's most of the area under the curve, right? That's a significant amount. Now you could check this in your calculator, right? So we could check this in our calculator by going over to second distribution. You pick 2, right? In this one, my lower bound would be essentially a negative infinity. So I could just do negative 10 to the 99. We saw that already, right? We saw that we could just do a negative 10 to the 99. My upper bound would be the negative 0.8, right? And then everything else stays the same. And that should confirm, yep, there's my 21 point, essentially 19 if we were to round, right? That's slightly more accurate in the calculator, right? And I could do the same thing here. I could do second distribution, go to normal, cumulative distribution function, sorry, CDF. I'm starting at negative 1.2. Sorry, it's been a long day of video recording and my brain is a bit fried. All right, I go to 1.6 and there we have it. And sure enough, I get the same answer. So again, that's just another way to deal with it if you want. All right, so let's talk some properties of normal distributions. So normal distributions are symmetric about the mean, right? So this is my mean. The total area under the curve is 1, which is 100%, right? That's why we're able to treat these areas as percentages, right? 100% would be the whole area. The mean, median, and mode are all essentially very, very close. They might not be exactly equal, but they're very close in value, the mean, median, and mode. About 68% of the data falls in the first standard deviation, so that would be 34 on either side, because remember that this is symmetric, so if 68% around the mean, it would be 34 on either side. About 95% of the data falls in 2 standard deviations, right? In 2 standard deviations, which is why we get a 14, 34, 34, 14. And then 99% of the data falls within 3 standard distributions. So when you hear that you're in, for instance, the 99th percentile of something, that means you're the person over here that doesn't even fall within 3 standard deviations, right? So if you're in the 99th percentile, that means that you are so far at the top of the curve that you are not even in those 3 standard deviations, right? All right, so for example 2, I copied this chart in from the last page because I thought it would be useful for us. And remember that in stats, you very often have the material in front of you. You're not memorizing as much in stats as you are figuring out how to apply information, right? So sometimes you have a ton of formulae in front of you, and it's about which one to use, which one's appropriate in the situation, how to logic your way through the situation. It's a very different brand of math than a lot of what you've learned. So if you choose to take AP Stats or you take stats in college, you'll kind of see that. So again, we have a lot of information in front of us. I'm not expecting you to memorize this, right? I'm expecting you to be able to apply it, not memorize, and that's a different skill set. So scores for a certain professional exam are approximately normally distributed with a mean of 650, right? So 650 is this middle line, right? And a standard deviation of 100, meaning one line out, that first standard deviation is 100, so that would be 650 to 750, 750 to 850, and so on, right? So A, what is the probability that a randomly selected test score is between 450 and 850? Well, if you picture that 650 is the mean, right, so this is my mean, then 1 standard deviation out is 750, and 2 standard deviations out is 850. Going in the other direction, 1 standard deviation out is 550, and the next standard deviation out would be 450. So what we're talking about here is we're talking about this exact situation. 95% of the data falls within 2 standard deviations. So the answer to this question, this is 2 standard deviations. The answer to A is 95% because approximately 95% of the data falls within 2 standard deviations, right? This is 2 of those little coach's whistles, right? It's 2 standard deviations, 2 standard deviations on either side, right? Out of 1,000 randomly selected people, how many would you expect to earn between a 450 and an 850? Well, it's 95%, right? So 0.95 times 1,000 people, right? Sorry, that's not 1,000. So 0.95 times 1,000 people should be 950 people. So again, you're not asked to memorize this. The idea is to be able to apply it. So in P2, the lengths of a certain bolt are normally distributed with a mean of 8 centimeters and a standard deviation of 0.01 centimeters. What is the probability that a randomly selected bolt is within 0.03 of the 8 centimeters? Well, 0.03 is 3 of these standard deviations, right? 3 of the standard deviation. Well, if you look down here at this information that we have, 99% of the data is within 3 standard deviations, right? That's not a 36, that's a 3 standard deviation. So A is 99% because it's within 3 of the standard deviation, right? So the second question is, if there are 1,000 randomly selected bolts, how many of them should be within that measurement? Well, 99% times 1,000 would be 990 bolts. All right, moving on. So there's a measure called a z-score, and I'm not going to go into this a whole lot, but essentially a z-score is basically how many standard deviations you are from the mean and in which direction. Okay, so the short version is, see how 70 is 2 standard deviations away and to the right? Its z-score is 2. See how 20 is 3 standard deviations away, but to the left, its z-score is -3. So essentially, it's the difference between the x value and the mean divided by the standard deviation. And so the idea is that z-score is a really easy, quick way to communicate where something is on a normal distribution, right? So again, it's essentially whatever the x value is minus the mean divided by whatever you're calling the standard deviation. All right, that's our z-score. And again, if you take a stats course, you'll learn a lot more about this stuff, but we're not going to spend a ton of time on it. So we're going to use a calculator for E3 and P3. As you can tell, I had to look up the calculator steps because I don't typically teach a ton of stats. So an airline finds that the travel times between 2 cities have a mean of 85 minutes and a standard deviation of 7. Now, just to point out, if I ask you questions about things that are 7 minutes away from 85 or 14 minutes away or 21, those are really easy questions to answer, because if you're a full standard deviation away, we can fall back on the stuff that we did up here where we said, oh, look, I know what percentages happen each standard deviation. But if instead I give you values that are not conveniently a standard deviation away, then we're going to have to lean on a calculator. So we're asked to find the probability that a flight from the first city to the second city will take 75 to 90 minutes. Well, here's why this is a problem. 75 is not 7 minutes away from 85. It's not any convenient multiple of 7. 75 is 10 minutes away from 85, and that's just not helpful. 90 minutes is 15 minutes away from 85, or sorry, is 5 minutes away from 85, which is not any multiple of 7. So again, we need a calculator to do this, right? So in order to do this, essentially what we're going to do is we're going to go over to that second VARS, and then we're going to go over to draw. So we're going to go to second VARS. We're going to scroll over to draw. And what we want is we want shade norm. Okay, now before we do this, one thing to keep in mind here is on your normal curve, you're going to want to set your y-axis. So let's go to y equals first. I'm going to turn off my plots from earlier. I'm going to clear stuff. And let's go to window. And I'm going to set my window to be some pretty small values, right? Because normal curves are actually really tiny, right? If you, most of the time, if you picture what they look like, because we're not talking about the actual test scores people get, right? We're talking about a distribution under the normal curve. The area is a total of 1. So you're looking at really small y values to get that area. So when we go to window, I'm going to go to window, and I'm going to set it to -0.02, right? And I'm going to set it to 0.08, right? Oh, sorry, I didn't mean to make that my x's. I take it back. My x's should be in this window. I want to make sure my x-axis is at least 3 standard deviations on either side of 85. Sorry, my brain is a little shut off for a sec. So I want to be within 3 standard deviations, or about 3 of 85. So that'd be 21 more than 85. So that'd be a 106. So I'm just going to go to 110. That's fine. And the same thing, I want to go, like, let's say I'll go down 30. Let's just say 55. That's fine. Around the mean. And then my y is going to be really small values because, again, what I'm finding is the area under the curve is a total of 1. That's going to be a really small curve, okay? So there's my window. I'm going to quit out of this. So what I want to do is I want to go over to second distribution, draw, and I'm going to pick shade norm, okay? Now, mine looks a little bit different than what you'll see down here in the calculator, but the lower bound is the lower estimate they gave me, the 75, right? The upper bound is the 90 minutes they gave me. The mean is the 85 they told me about, and the standard deviation was 7. And if I do that, it's going to shade this for me and give me a probability, right? And so it gives me an area, right? And if I screenshot that for you, it's going to give me this area. I could have probably picked a better y value. I didn't need it to be quite that high. So if I screenshot that and drag it over, what that means is that's the area I get. So the percentage is this guy right here as a percentage. That's a 68.591% chance, right? And you can see that I have that down here too, and I did a bad job of picking a window. I think that when I go to my window, oh yeah, see I picked 0.8 and I didn't mean 0.8. Sorry, I meant 0.02. I think I put the 0 in front and didn't notice. Sorry. That'll give me a better window, hang on. 0.08. Sorry, that's what I was aiming for, and just sometimes my brain is slow. Didn't do anything too crazy there. Let's go to VARs, not VARs, second VARs. Let's go to draw, shade norm. We want, it was 75 to 90 with an 85 mean and a 7 standard deviation. There we go. Okay, so that's better. Sorry. So, and you can see that that's similar to what we get here. I picked slightly different x values than they did, but you get the gist of it. So again, we can still see that that's the number that we're going to want to get. You can do the same thing. So there's other ways to do it. They list another option for finding that area, right? But I think that by far this is, you know, a pretty easy way to do it. You'll notice that in the calculator, if you did it the other way, it looks like if your calculator is a little bit older, it's going to look like this. It's going to look like shade norm, the min value, right? The max value, the mean value, and the standard deviation. We'll just say that. And then I'd hit enter, and it would do this, right? But again, if this were a slightly older version of the calculator, and I have mine set on the oldest version, it'll let me set it at, but apparently it's not old enough to do that. So you need a calculator to do this because, again, the numbers they ask about aren't within a single standard. They aren't a single standard deviation or 2 deviations. It's not a multiple of 7, so that's the idea. So let's go ahead and give one more a try. Again, I'm not going to make you do this. I just want you to get the gist of it. Yeah, so let's go ahead and try this. So a bus route takes a mean of 40 minutes, right? So that's our mean, right? There's your mean. To complete with a standard deviation of 5 minutes, right? That's your standard deviation. Assume that completion times in the route are normally distributed. Find the probability it takes 30 to 45 minutes, right? So again, what you're going to do is you're going to go to shade normal, right? And you're going to put in the minimum, which is the 30, to the maximum, which is the 45, the mean, which is 40, and the standard distribution, which was 5. Now, do you need to do it for this one? No, because if you notice, 5 standard distribution means you could actually figure this out. So you could do it this way, but here you can do it maybe a little bit more with some logic, right? So these are standard deviations. You could do it a little bit more with figuring out the logic of how this is going to work because it's 1 standard deviation on one side and 2 on the other. So you could do it more by hand here, but I don't know why you'd have a huge incentive to do that. So I'm going to go to second distribution, over to draw. I'm going to pick shade normal. I want to go from 30 to 45. The mean is 40, and my standard deviation is 5. And I'm probably going to have to go to my y equals, actually. I take that, or to my window, rather. I take that back, because here I was centered around a mean of 110, and that's not what I want, right? The mean here is 40, so I'm just going to go from 0 to 80. That should pretty much cover it more than I need it to. 0 to 80. And we can go by tens. That should be more than enough space for me to see what I want to see. So I can quit out of that. I'm going to go back to distribution, draw, and again, my min is a 30 up to 45. Mean was 40, and my standard deviation was 5, and that should be there, all right? And so again, if we screenshot that, you're not expected to know how to do this by hand. It's absolutely fine to have to look this up. So we would be looking at an 81.859 or 860% chance. And that's what we get from that number with the area. And that is it for 12.5, or sorry, 12.6.